Now, I am going to talk about, in this lecture, classical interpretation of photoelectric effect. That's a classical interpretation of photoelectric effect. So, interpretation of photoelectric effect. So, according to classical mechanics, or the classically, when light is incident on a metal surface, when light is coming, and light is coming in the form of a wave, so, and it is made to incident on the metal surface, so then what will happen? The electron inside the metal, it starts vibrating with the electric field vector of the incident light. It has electric field vector E. With this electric field vector, this starts oscillating, right? And it will give its energy to it, and after some time, it will take off from the metal. So, as the light accumulates on the metal surface, the electric field vector and hence the vibration amplitude increases, and at a certain value the electrons are taken off the metal. Electrons are taken off the metal. So this is a way that how we look at this classically. But we are not able to explain so many things classically regarding this. So first is the instantaneous emission. The first problem is it was not able to explain the instantaneous emission. So problem with the instantaneous emission. With the instantaneous emission. So it's a problem. So for this, let us take an example. So take a metal whose work function is 2 electron volt. Let us assume, and consider a light of energy 10 raised to power minus 4 watt per meter square fall on the metal surface, and let 10 raised to power minus 10 be the size of the atom. Then energy received by the electron it can be 10 raised to power minus 4 watt per meter square into cross section area of atom. So that means it is 10 raised to power minus 4 into pi r square. So it's the size of the atom. So what it will be, 3.14 into 10 raised to power minus 24 watt. And this can be converted into joule. So what it will be? It is 3.14 into 10 raised to power minus 24 divided by 1.6 into 10 raised to power minus 19. So it is roughly equal to 2 into 10 raised to power minus 5 electron volt per second. Now let us calculate time taken by electron. Now time taken by electron to come out of metal surface. So it is equal to T is equal to 2 electron volt, it is the work function divided by the energy. So it is 2 into 10 raised to power minus 5 electron volt per second. So it is nearly equal to 10 raised to power 5 seconds. So it will take 10 raised to power 5 seconds for the emission of electron. And if we convert it into 10 raised to power 5 into hours, then how many hours it will take? So let me try to convert 10 raised to power 5 second into hours. So 10 raised to power 5 seconds. Let me convert it into first of all minutes. So it is 1666.66 minutes roughly. Then I can convert it into hours. So it is roughly 27.27 hours. So it is more than 1 day will be taken to knock out the electron classically. So this is the major drawback which we are not able to explain. Then another thing which people observe, that photoelectron should not be ejected. Should not be ejected below the threshold frequency whatever may be the intensity of incident radiation. And third thing is that maximum energy of ejected electron increases linearly with the frequency of light. Frequency of light. And remain independent of intensity. So that means EV naught is basically, it's like this. It is nu naught and this one. So that's what are the three observations which classical theories cannot able to explain, right? So later Einstein tried to explain the photoelectric effect. So in the next lecture I will talk about that how Einstein's approach explained the photoelectric effect.